All right, welcome. Discrete math. Here's where we are. Last class, we basically kind of like just went over homework for almost all of the period, but like mixed in with that was like some teaching, some very important theorems, such as that in any graph with n vertices, there are two vertices of the same degree. Classic fact.
And the odd cycle.
And the main thing that we did that took like 40 minutes was the proof that a graph is bipartite if and only if that has no odd cycles. And then towards the very end, we were going over the homework from section 10.2. And then I made a little tiny video. Did anyone watch it? I kind of said you could like watch it or not. It was like a little bit of a boring video. I was talking too much. Like it could have been half as long. But you thought it was fun? Or you didn't watch it?
Well, I
just read the book?
Yeah.
Okay, cool. Yeah. I don't think what I said was particularly any better than Gossett. Although instead of giving an example, he like proved it in general with like induction, which I thought was like obnoxious a little bit because it doesn't really help at all. Anyway, woo! So 10.2. Can we actually spend 10 minutes on the homework? Because I feel like that's all it needs. There were the problems I am talking about. I did this homework too. Was like there were a bunch of questions. There were a bunch of questions that were asking us to like draw various like trails and circuits and stuff. But then like maybe we could do a couple of these like how connected is the graph. Also, can you point the camera? Well, I don't know what you want to do with the camera. What do you want to do? Like did I assign 6A?
That's right.
I feel like I did assign 6A. Yeah.
That's right.
Yeah. This is the famous Peterson graph.
Wow. Okay. No, I just like totally forgot I was on the man.
So la 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 6A. Woo. It looks like this. There's like boom, 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 boom. I can't remember why this is so famous. I think it's like a famous counterexample to some purported graph theorem that turned out to be false. It's like got some. I made an entire thing one year. Wait, hold on. I had this whole notebook called Book of Graphs that they made 2 years ago, and it's just graphs. Very first graph. Boom! I didn't even know that was going to happen. The Peterson graph. It's important. Let's put this one online. It's important to know all your graphs, man. The Peterson graph, the dodecahedral graph. This is the graph that describes your relationship between all the points on a dodecahedron. The icosahedral graph, the Tada graph. I don't know what's up with that, but that's like got some property. I think it's like regular in that every vertex has 3. I don't know what the hell that is. It's like a cubic graph. It's like a cubic graph, so-called cubic graph. Every vertex has degree 3. I think it's like the smallest graph that's cubic, but like doesn't have some property. I don't remember. The Nauru graph. I don't know anything about that either. The Haywood graph. I know a couple things about that. Klein graph. The Pappas graph. Coxeter graph. The Dick graph. I believe that's how you pronounce it. Dyke, maybe. It's Dutch. I should know how to pronounce it. I can't remember. K8, our old friend K8. Folkman graph. We're just wasting time now. K7. More graphs, man. The Lupikine snark. The first one. There's a whole category of snarks. Horton graph. You could just spend your whole life on just studying and learning all the graphs, man. The star graphs. Holt graph. Meredith graph. Ellington, et cetera, et cetera. All right, I'll just leave this out, and you guys can peruse this whenever I start saying something boring. Anyway, here we go. The Peterson graph question. The question was, I set you up for that. What is the connectivity and edge connectivity of this graph? So there's really two separate questions. What is the vertex connectivity? What is the edge connectivity? What did you get? Yeah, for which one? For both. Yeah, I think that is just true. For vertex connectivity, I guess it's like how many vertices do I, wait, yeah. How many vertices do I have to remove for this graph to be disconnected? And like, I guess like a bunch, right? Because if you remove any one vertex, it's like still connected. If you remove any two vertices, also does everyone see how this graph is like totally symmetrical, right? Because this star on the outside could this star on the inside could very well be like on the outside. Is everyone seeing it? Perform like a, then that pentagon in the outside could very well be on the inside. And so like, there's really no difference between the relationships. And then you could also like turn the pentagon into a star, but if you turn the pentagon into a star, then the star turns into a pentagon. You may or may not see that. I may or may not see that. It's just, you have to just convince yourself that this graph is completely symmetrical. And therefore, how many vertices do I have to remove to make it disconnected? Well, I guess I have to remove 3, right? Like if I remove like this one, and this one, now this point will be disconnected, but like I can't do it in any less. Any 2 vertices that I remove, I can still make my way around. Would anyone like to give an argument of this? Or is it just kind of like, true? Just do it? Okay. I mean, some argument should be available that was like high level, but I don't have it on the spot for why 2 won't be enough, right? That's what you have to say. Once you give me 3 vertices, for which the graph is disconnected, you've established that the vertex connectivity is 3 or less, right? So to really establish that it is exactly 3, you didn't have to do this proof, you just had to say what you thought the answer was, but to establish that it's really 3 and not, say, 2, there should be some sort of proof that like 2 is insufficient. So he raised his hand, so what do you got?
I think if you take any vertex, it's like connected to 3 other vertices. So if you remove those 3 adjacent vertices, then you have like that vertex by itself.
So take any vertex, like which one on the top, remove it.
Yes.
Okay.
Remove all the ones adjacent to it.
Remove all the vertices adjacent to it?
Yeah.
All of them? Or what do you mean all of them?
Yeah, there's only 3 vertices adjacent to it.
Okay.
So like if you move down one of those lines, remove that vertex.
If you're saying if you remove it,
Yeah.
it's still connected.
And then you remove like for each of those lines, you go down and you remove like a vertex that's connected to the top vertex.
Yeah. Oh. Hold on. That was just like on video. Stop doing that. Good. Yeah. Wait. I 30% followed that. Yes.
Because the graph is regular, you
Uh-huh.
have to remove at least the least degree, or exactly the least degree. Because if it's not regular, it can be less than the least degree. But since it's regular,
Is that just true?
I don't have a good explanation, but it's just like.
Okay, wait, this is cutting into our 10 minutes, so let's move on. What is the edge? It's like taking half the 10 minutes. What's the edge connectivity? Also 3. Yeah, I think this one's like, more clear, right? That to disconnect any point from the rest, you need to remove like 3 edges. So it also has edge connectivity. I thought actually 6C was harder. What'd you guys get for this one? I got 4 for both, but I put some effort into it. And I just kind of drew a bunch of pictures. I got nothing more to say about that. Stop with the memes. Put the memes away. Good. Next, let's do like one more problem from this homework, which I think is all we need to do. How coherent was this whole explanation of adjacency matrices and stuff like that? Oh, you want to see something really awesome? Wait, do you guys read Les Mis in high school?
Yeah, like some of them. We don't read the
Like,
whole thing.
you read like an abridged version?
We read an abridged version, we don't even read the whole thing.
Okay, but some of you read it in high school, like part of it.
Yeah.
Or you've like seen the movie or something, or the play, or the musical.
Yeah.
I was just like screwing around today during my calculus test. Should I put them on the screen, or should I just not even bother?
Do it.
It's the adjacency matrix for every single character in Les Mis.
How do you classify vertex?
So the full, it's a good question. So I'm gonna turn on light up the full screen down. The full book is like 1,500 pages long or some crap like that. And where's this guy? The full book is like 1,500 pages long, and and it's divided up into chapters. Some of the chapters are quite short, like only maybe say 10 pages, 20 pages. And so take every major character, and yeah, it's quite pretty, huh? Take every major character and create a matrix where each of those characters is the nodes. Yeah? Say yeah. Okay, and now create the adjacency matrix and define two characters as adjacent if they appear together in the same chapter. And the chapters are very, very short. Now this book is notoriously long because he kind of just kept writing and kept writing and kept writing for like 30 years and just never stopped. And he was like in jail for a while, he had nothing else to do, etc., etc. So it's more like 5 novels in one, like it just goes on and on and on. Like the main character of the first 500 pages like dies on page 500, sorry, spoiler alert. And then the book just keeps on going. And like arguably the second main character of the book isn't introduced until like page 750 or something. So this is something that people have been interested in. And here's what we have. This is the adjacency matrix organized by just alphabetically. So like just organize the names of all the characters alphabetically, and here we have the matrix of all the relationships. But perhaps more interestingly would be by frequency. So now just take order the rows and the columns by like who is the most who's the character who appears most often. Okay, Jean Valjean, who is essentially the main character of the book, is in like more than half of the chapters, although not all of them, which is kind of interesting. And here you see everyone's relationship to him. But there are certainly like many chapters in which he doesn't appear because these characters don't share any chapters with him. In fact, all these characters. But then what this guy does is it also has this algorithm to do it by cluster. I'm not sure exactly what the details are, but this sort of reveals the structure of the novel as being really composed of a bunch of different novels, because all these like yellow characters all sort of like appear together often. So this is like some 300-page section of the book where these characters have like a whole storyline, and then most of them like don't appear anywhere else. Follow? So Jean Valjean, who is this horizontal and vertical line, sort of transcends all the various like subplots of the book. Cool? I thought that was nice. Adjacency matrix is really important. Oh, wait, there's another famous thing I do every year. I don't know if this class is mature enough for it, but I almost hate to do this on a day when not everyone's here because it's so wild. But one of the most famous uses of graph theory is these researchers went into a high school somewhere in like Ohio or something, and hold on, how do I even Google this? This is very PG-13. Let's see, so graph of teenage Ohio study one, something like that. Yeah, it's really famous.
Is there something
It is, I should have the link somewhere, but I like don't. Here it is, boom. Yeah, so here we go. If you are what's the word for someone who studies the spread of disease, like epidemiologist, is that a word? I think that's even the right word. That is the right word, yeah, good. So graph theory is extremely important if you are studying like disease and how diseases spread, and well, I mean, it's sort of obvious, right? And you're interested in, there are these, whatever, what's the most recent thing that seemed like was going to kill us all? Measles is happening right now. Yeah, don't go hang out in the Brooklyn or don't go hang out. Well, I mean, you can, I guess. Good luck. What was the one from like 4 years ago? The one where they just said straight up don't go to South America. No, Zika. Yeah. So my brother's actually a doctor. He works in New York City, actually with the Orthodox community. In New York City, not them exclusively, but in that general region of Brooklyn, and he's like one of the experts on Zika, and it became a huge thing. And so you want to know things like, for example, when you catch Zika, on average, how easy is it to spread to other people and stuff like that. All right, well, if you're studying how STDs spread, then you got to figure out who is hooking up with who. And so what they did is they went into this high schools basically, and they these researchers in the 90s came up with they interviewed extensively over a period of months every single person in this high school, and they constructed a graph of all the people who had sex with each other. And it ends up looking something like this. So what we see here are, I think, like there are also just like many vertices of degree 0, not depicted. But all the vertices not of degree 0 are depicted. So first we have 63 of these, and this was probably like, I don't know whether this was ever or over the last year. 63 just heterosexual couples. Then you have,
Wait, what are
what's up? Yeah, they're just like not here. That's vertices of degree 0, not depicted. Vertices of degree 0, not necessarily lonely, just not sexually active yet. Then you have like, certain numbers of these 9 in particular of like this, where so there's, one woman, whatever, girl who has at some point over a period of, whatever, had sex with 2 different boys, one of the sort of reverse. Then, you guys can read, right? 2 of these, 2 of these. And then there's some like situations where like, then, what you would fear if you were an epidemiologist is that like everyone would be related to everyone else, because if there's some kind of STD, it would like spread horribly. But actually, what they found is that due to like the sociology of teenage or whatever human relationships, you actually have very few cycles. Note, because like you don't want to date your like ex-friend's ex or whatever type situation, I think, or I think I'm not saying that right. But you do have this one giant kind of connected component of the graph, but it's like not. It doesn't have as many connections as you might think, right? There are some cycles, but not as many. And there's like an entire paper. It's fascinating. I'll put the link up on the. What's up? There's a couple cycles, but like.
Also not
I don't know.
It is not by. I guess it is. I don't know what.
You can see a triangle on the like top right.
Are there some homosexual
yeah.
relationships depicted?
Yeah.
I don't see any.
Yeah.
Where?
That triangle right there.
Oh,
No, no, no,
oh,
up there.
here.
That one, yeah.
This one's a triangle.
Oh, true. Yeah, because. Yeah. Good. All right. Anyway, that's fascinating. That's like a famous thing. This is like a famous paper. And Chains of Affection. Good title. This could be your SRP. Good. Wait, can we just skip going over the adjacency matrix? I feel like it was like self-explanatory. Yeah.
Yeah.
Good. How far did I go over the 10 minutes? Was anyone even timing me? They don't take me seriously.
I was looking at the clock. I went 5 minutes over.
That was like 17.
That was
17 minutes, not too bad. All right, what's another famous way to change your mind? Turn lights up. What's another, famous problems in graph theory? How related are the characters of Les Mis? Just kidding, that's not a famous problem. Second famous problem of graph theory. What are the teens in Ohio in the 90s doing with each other? Third famous problem of graph theory. Wait, did I just like close it?
Yeah, you did.
I am
Control
dumb.
Shift.
Hold on, wait. Boom. Alright, so, I spent the last period kind of reading about it. So you may have heard of this before. This is like a cliche way to introduce the very topic of graph theory. And thus you may have heard of this in like middle school or something. And in fact, Gossett opens the chapter on graph theory with this story. It is appropriate to do that because this is how graph theory was invented. Okay, so it goes something like this. There's a city called Königsberg, part of Prussia, and at the time Euler is living in this is it was sort of like its own. Well, it's a city in Prussia, which is now in Kaliningrad, Russia. It's that little piece of Russia that's discontinuous from the rest of Russia. You guys know what I'm talking about? Woo! I'm like, yeah. And in the 18th century, there was this river, the Pregel River. And this is like a picture roughly of the aerial view of the city at the time that Euler lived there. I think he lived actually I think he actually did live in Königsberg, I think, at the time, not sure. And so here's what you have. You have like the north bank of the river, or I think it was north. You have one bank of the river, you have the other bank of the river, but then you have these two very large islands. And, okay, there are two bridges taking you from one bank of the river to the island, two bridges taking you from the other bank of the river to that island, and then this other sort of large kind of peninsula type island thing, which is like gets bigger and goes far away, and there's a bridge connecting it to the island and to the other banks. So seven bridges in total. And these bridges are all like, beautiful and elegant and all give separate views of the whole river and blah, 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 the city. And so it became kind of like a question. Hey, can you take like an evening stroll and walk across all 7 bridges precisely once without repeating? I've also heard this described as they wanted to stage a military parade that went through the city and crossed all 7 bridges, but one of those two is made up. I can't remember which. So like you're thinking, okay, I can probably do this. Well, let's go, right? You start here and you go, I don't know, here, and then cross that one, and then wait, I can't go back because if I go back, I'm stuck, right? Okay, so I better go forward. But now I gotta go back, but now how am I ever gonna use that one? Seems like I can't now, right? So I screwed up, so okay, try again. All right, good, take a couple minutes. By a couple minutes, I mean 20 seconds.
You have to go to the impossible.
You have to, the goal is to take a walk and cross all 7 bridges once. So don't skip any bridges. And don't walk across any bridge a second time. It's just not possible.
Just walk all the way around the river.
Buy a boat. It's pretty good, right? So the 7 bridges, right? These two bridges, bridge. And the question is, is this all like on screen? So you can tell if it was. It is good. All right, all right, any person with a little bit of persistence can spend, say, 10 minutes and just convince themselves that this is just not possible. So it is fact, it is not possible. Can we get a proof of such a fact? Well, Euler himself constructed a proof. And in the construction of his proof, he just invents the entire mathematical field of graph theory. And so what he says, first of all, is, okay, the particular sort of geometry of the city is sort of irrelevant. What we really just have are like some landmass, some other landmass, and these 2 other sort of things. And all I need to do is all that's sort of relevant is how many connections there are between the landmasses. And also, once you're in a particular region, like a particular side of the river, like what you do on that side of the river is like irrelevant, right? And so what's happening here is this abstraction away from like the problem itself to like, we might as well, once you're on this bank, you're just on this bank until you cross another bridge. And so you might as well consider this bank of the river to be like a single point. And so I think that you see quite naturally that what Euler does is to treat the 4 pieces of land as sort of vertices, and the only thing that's relevant is how many bridges there are between those landmasses or edges between those vertices. And now the problem becomes sort of more precisely defined as, given this particular graph, 4 vertices and 7 edges, the multi-graph in fact, like can we come up with a trail is Gosset's term for a walk that does not repeat edges, agree? Which not only does not repeat edges, but which uses up every edge. And now that we've abstracted the problem to one of graph theory, now it seems that there should be like some sort of like a formal proof of this fact. And so not only was this the beginning of graph theory, but like this Wikipedia talks page talks a lot about how it was very influential in the sort of history of mathematics because it was one of the first times in which we began to see sort of a pre-topology notion, and then we begin to see that like the specific geometry of the situation is not important. All that's important is like the connections that exist between them and like the way in which they're related. But the shape doesn't matter, only the sort of more general sort of structure. Okay, good. So now we'll actually turn this off. So let's do it. What seems to be the theorem? Why? Oh, we forgot that whole part. Why can you? Why have you convinced yourself, or maybe you just know because you've seen this before? It is pretty famous. Why is it that you can't do this walk? And let's see, this graph has even come up like in a couple homework problems and stuff, right? It's like vertex, vertex, vertex. There are two bridges between these two, and then there's like another one over here, and I guess it's like zone, zone, zone. So what's the argument? So would someone like to give it to me who either came up with it on the spot or who knows this because it's like famous? Whew! Yeah.
And one of the vertices has odd degree. So you have to go in by one edge, come out by another edge, and then if you want to traverse that last one, you're already out, so you have to go back in on the third edge, and then there's no way for you to get out. So you need even numbers, so you always have a way in and a way out.
Yeah, that's the gist, right? The gist is the super casual, like, I'm giving a math team presentation to 7th graders type way of talking about this is, yo, consider the degree of all the vertices. What's the degree of this vertex? Well, it's degree 3. What's the degree of this vertex? Oh, damn, it's also degree 3. This is also degree 3, and this is degree 5. Well, that seems really bad because you generally don't want an odd degree vertices because, look, if you have an even degree vertex, then that's good. Because every time you go in to that vertex and back out again, in other words, every time you pass through that vertex on a walk, then you use up one edge going in and one edge going out, right? But if you have an odd degree vertex, then you have this stuck problem, right? If I'm headed towards, if I call this V1, V2, V3, and V4, well now consider what happens as I'm walking through V1. Well, I go into V1 and back out again, but I use up, as I do that, I use up precisely 2 edges. So, but somehow I need to go back to V1 to use up that last edge, and I just can't. So what's my only conclusion? If I have an odd number of vertices at V1, you have to either start or end there, right? The only way to have an odd vertex is you need to either start or end there. Okay, so I can start here. That a little bit solves my local problem because now if I start at V1, then as I leave V1, I use up 1, right? Edge. You guys following this? This is like pretty easy. And now I'm going to pass through V1 one more time, and when I pass through V1 one more time, I'll use up 1 edge going in and 1 edge going out. But the problem is that I have 4 vertices of odd degree, and so that just can't happen. So would anyone like to make a conjecture or summarize something they already knew?
If you have more than 2 odd degree vertices, you can't make a trail that uses all the edges.
If you have more than 2 vertices of odd degree, then it can't be done. And the it is to go through using up every edge exactly once. So just to summarize the vocab again, trail, which is Gosset's term for a walk which uses
No edge twice.
which does not repeat edges, right? So trail is a trail doesn't repeat edges. A Euler trail is a trail which, or some people say Eulerian, so I don't know, whatever. An Euler trail is a trail that not only doesn't repeat edges, but it uses every edge. Uses every edge. And then the other thing you might ask is, what about one that starts and ends at the same place? So like a parade, so we call this an Euler circuit. And as we know, a circuit is a closed trail. Yeah, that's right, yeah?
Isn't that connected to the Hamiltonian pattern?
is that's the other thing we're going to do today. But I think it's not directly related. So a circuit is just a closed trail. I hope I have that right. Yeah, I'm pretty sure I do. Yeah. So a trail doesn't repeat edges. A circuit is just like a trail, but it starts and ends at the same place. An Euler trail uses every edge, and an Euler circuit also uses every edge, but starts and ends at the same place. Okay, and the sort of, I'm going to get a new marker now, it's getting serious. The big theorem, what Euler did was to prove something more general, that under precisely what conditions we have a Euler circuit. And the answer is when there are no vertices of odd degree. All right, let's do it. It's another classic result of graph theory. Woo! Theorem. For a connected, and why do we insist the graph be connected? Why is that a reasonable thing? Yeah, then why is this? Come on, man. If it's disconnected and there's just no freaking Euler trail possible, of course, right? Because we need to use every edge. Here. So for a connected multigraph G, we say that G is Eulerian. If and only if every vertex has even degree. So I'll use Gosset's terminology, which is G has an Euler circuit. Some people say that the graph, therefore, is Eulerian. If and only if G has no vertices of odd degree. All right. And this is really like, two proofs. One of the directions is pretty straightforward. It's the other direction that's quite hard. And this proof is in the section. It's in the textbook in section 10.3. But I don't like that proof so much. You can read it, maybe you like it, but I don't like it. Okay, here we go. What is the easy direction? I guess the easy direction is the forward direction. Yeah. So the forward direction is let it have an Euler circuit and then show that there cannot be a vertex of odd degree. Okay. So suppose suppose G has an Euler circuit. All right, well, what is an Euler circuit? An Euler circuit, let's call this Euler circuit, well, this proof is like not even a proof. I'm reading this right now. It's just like, he just one-lines it. But I think we can too, right? Suppose G is an Euler circuit, well then what does that mean, right? What that means is that we have some trail, let's call